So let's evaluate this part here using two techniques. We're going to do the parallel axis theorem first. Then we're going to do the same problem using the whole minus the whole technique, and I hope that we get the same answer. Whole minus the wholes can't be used in all cases, but in this particular case it can, and we'll talk about the reasons why as we go. All right, so first part, parallel axis theorem. What we want to do is break up this part here into four logical pieces that make some sense. So in this case, I have a part here, then here and here. You can see where they've drawn the lines on the figure for you, so I made that kind of easy. What I want to do is I'm just going to label these here. I'm going to call this part 1 and part 2, this part 3 and part 4. Now, what you might be able to see is that parts 3 and 4 are both symmetric about what is already the x prime or centroidal axis. So we don't have to use a parallel axis theorem on these two. These two are the same distance, but because they're not on the x prime axis, then you have to transfer them using the parallel axis theorem. So let's just set it up. I about x prime is equal to the sum of ig, or this of each part, plus AD squared. Okay. Let's see what our distances are. That's probably the next thing to do. These two guys need to be moved that far. And what is that distance? Well, this one also has the same distance down there. Let's look at the picture. This is a 200 millimeters tall, which means that's 100 millimeters right there. This is 30 millimeters thick. And so what I'm looking for is from the inside here, there will be this part right here is 15 millimeters from the edge. This is 100 millimeters from the edge up to there. That makes this distance 85 millimeters. And the same would be on the top, 85 millimeters. Now, let me also say in terms of units, in the metric system, millimeters is the standard unit of measure for this type of exercise in the metric system. We're using SI units. So don't use meters, use millimeters. All right, so D3 and D1 and D2 are equal to 85 millimeters. All right, let's go ahead and put these in here. For parts 1 and 2, I have to use the parallel axis theorem. So I'm going to say that those are BH cubed over 12 plus AD squared. Now, again, those are exactly the same. They have the same area and the same distance. So for parts 1 and 2, I can just multiply it by 2 instead of do the same thing twice. All right, how about the other one? It is going to BH cubed over 12, and parts 3 and 4 are also exactly the same. So I can just multiply it by 2. So let's just move this up a little bit. All right, so let's put some numbers in and see what we got. For parts 1 and 2, the base is 300. The height is 30 cubed over 12. The area is going to be 300 times 30. That's the area. And then the distance I'm moving it is 85, and that's squared. All right, and that's times 2 because I got 2 of them. All right, let's try parts 3 and 4. Those are going to be, the base is 30 and the height is 300 cubed over 12. And again, I have 2 of them, so I'm just going to multiply that by 2. Calculating that all out, you'll get 1 I about x prime is equal to 171 e to the 6th millimeters to the 4th. So again, using the parallel axis theorem for these are already on the axis, so that means their centroids is on the centroidal axis, so you don't have to transfer it using parallel axis theorem. All right, let's use this do the same problem using the. So here we're going to consider the WHOLE and subtract out the HOLE. The reason this works is because both of the whole and the big hole, WHOLE, are both symmetric about the x prime axis. So in that case, you can do this. And if that's, you'll have to look and be kind of clever about that investigation sometimes, and we'll talk about some obvious things to look for. But let's just go ahead and calculate it out. Let's choose that. I about x prime is equal to bh cubed over 12 of the whole minus, in this case, bh cubed over 12 of the whole. So let's see what we got there. The base of the entire thing would be 360. The height of the entire thing would be 200. Minus the whole, which is 300 is the base. The height being 140 over 12. Now, where did we get 140? It is this 200 minus 2 times 30. So this inside dimension here is 140. Anyway, get your calculator out and prove me wrong here, but this is 171.4 e to the 6th millimeters to the 4th, which again is the same answer that we had on the prior page. So in this case, whole match to holes is a little faster. Again, recognizing when you can use it sometimes is the challenge. Well, let's do this one. This one, again, I want to calculate the moment of inertia about its centroidal axis. But in this case, I don't know what the centroidal axis is. So we need to find a distance from a reference to the centroidal axis. And we're going to use the table method to try to figure that out. So in this case, I'm going to label a couple of parts. I'm going to label this part 1, this one part 2. And I say that this one has a centroid, which will be going down to that one, and I'll call that D2. This one has a distance going up. I'll call that D1. We don't know either of those distances right yet because we don't know the distance y bar. That's what we're looking for first, is y bar. So let's set up the table method. I'm going to say part 1 and part 2. And I don't care about the x tilde because everything is symmetric already in the x-axis anyway. And besides, I don't really care if it's symmetric in the x-axis because I'm only looking for the x-prime axis as far as my centroidal axis in this direction. So all I really care about is y bar. All right, so I have an area and then y tilde area. All right, so what is the distance from my reference down here to the centroid in the y direction of number 1? Looks like that is half of 30, so that's equal to 15. The area is 30 times 150, and so I get a value here of 67,500 as my y tilde area. From my reference up to part 2, I go up 30, and then half of 150. So there'd be 30 plus 75. The area happens to be exactly the same here. It is 30 times 150. They're not always going to be the same, of course, but I get a 472,500 here. Now we're going to add these together. Again, I don't care about that one. I care about this one and this one. All right, so let's add those together. That'll give us 9,000, and this is 540,000. All right, I can find y bar is equal to the sum of y tilde area over the sum of the areas. So that's equal to 540 over 9,000. That gets me 60 millimeters. Okay, so that gives me 60 millimeters up to there. Now let's find out our distances. These are the distances for using the parallel axis theorem. So D1, which is on the bottom down here, if this distance here is 60, and this distance here is 15 up from the middle, or from the very bottom, it gives me D1 is equal to 45 millimeters. D2, I go up from here, 30 plus 75, so that's 105, I believe, right? 105. Then I go down to 60, so that also is 45. Again, not very often are you going to get problems as symmetric as that, but this is a fundamental problem in their textbook, and so sometimes they give a little easier shapes for that. All right, using the parallel axis theorem, let's see what we can find as far as the moment of inertia about our newly found x prime axis. So I about x prime is equal to the sum of ig plus AD squared. Okay, so that's going to be equal to BH cubed over 12 plus AD squared of part 1 plus BH cubed over 12 plus AD squared of part 2. Okay. I think I can keep everything on the page here. All right. Part 1 is the base part. So let's equal to, that's going to be 150 is the base, 30 is the height. The area is 30 times 150, which is 4,500. The distance we're moving it is 45, and that's all we need for that. All right, add that to part number 2. In this case, the base is 30 times 150 over 12. The area here, again, because it happens to be the same dimensions, is 4,500 times 45, again, squared. Make sure you don't forget that squared term because this is really commonly forgotten, I guess, by students. Multiply all that out, you get this is equal to I about x prime is equal to 27 e to the 6th millimeters to the 4th. So this one here is using the exact same technique that I just used, except that it is not uniform about the y prime axis. In other words, this is different on this side than the other side. We actually don't know where the y prime axis is because because we haven't calculated that yet. But we don't really care about that. All we care about in this case is just what happens about the x prime axis. Then the question will tell you what you need to be looking for. But in this case, find the centroidal axis first. Then we're going to use the parallel axis technique to do that. Again, this is just a little bit different here. So let's first of all divide this up into parts. You have a little bit of a choice here, but I'm going to call this part 1 and this one part 2. Then using the table technique, let's see if we can find out the y prime, which would be the distance from the bottom up to the x prime axis. So parts 1 and 2, y tilde area, y tilde area. All right, so the first part over here is over here. Let's put our centroid right in there and the centroid of that part right there. What we want to do is go up from here up to the centroid. That looks like, since this is total of 7, that goes up 3.5 inches. If you look here, if you look at the area, it is 2 by 7, so that's 14. So that gives us 49 over here. All right, on this side over here, we're going up to the centroid, which is 1. Now the distance, or the area here, is a little bit different. It is 2 by 6, so that's going to be 12. That's going to be 12. All right, add those two together. You got 14 and 61. So you get y prime is equal to 61 over 14, which is equal to 2.346. All right, so that's 2.346 inches to the x prime axis. All right, now that we do that, what we're looking for here is we got some distances. That's going to go down to there, and this one's going to go up to there. Now we can pre-compute those things, or I can show you just a little bit of a faster approach as we go ahead and just write this thing out. So again, we're going to look at I about I prime is the sum of the two pieces. Again, we're going to have BH cubed over 12 plus AD squared of number 1 and of also number 2. So let's just go right in the numbers and see what we got. So for part 1, I have base is 2, height is 7 over 12. I know that the area is 14. The distance is actually pretty easy to see. It is the distance, the difference between y tilde and y prime. So again, you can pre-compute them, or you can just write them out like this: 3.5 minus 2.346, and that's the quantity squared. Then we add that to the other one, which is base is 6, height is cubed, or 2 cubed over 12, plus the area. In this case, it's 12. And the difference, or the distance, is going to be this minus this. Now, it doesn't matter if you go that minus that or this minus this, because when you end up squaring it, you'll get a positive number anyway. So in this case, it is insensitive to which you put first. But I'll put 2.346 minus 1, quantity squared. And you end up calculating all that out. You get 101.5 inches to the fourth.